Hi everyone, this is lesson 21 and we're going to learn about energy. So we're going to begin our study of energy, and it's also related to what is the term we call work. Okay, so it's a little bit different from what we think of work as in English, but we'll get into that and how it's related to energy. So the objectives for this lesson are to determine or calculate the amount of work done by constant forces as well as variable forces. And then we'll also learn to quantify the energy due to the motion of an object. So what exactly is energy? Well, probably the way I like to define it, the easiest is simply the ability to do work. Okay, so in English, that kind of makes sense. You need some energy to do some physical work. And so there are several types of energy. And so remember, this course, we're learning about mechanics. And so there's two types of what we call mechanical energy, and those are the kinetic and potential energy. So those two combined make up what we refer to as mechanical energy. All right, and there's also thermal energy, which we'll learn about in Physics 152. So there's that we're going to leave that type of energy to that course. And we'll briefly mention it a little bit here because it does come into play sometimes when we're dealing with friction. There is some thermal energy, but we're usually going to ignore that in this course. And so kinetic energy we call energy of motion. Okay, so you can probably see that in the word kinetic there. So kinetic has to do with motion. Okay, so there's energy when an object is moving, it has energy. Okay, and then potential energy is essentially stored energy. And so we can store energy in many places. We've seen the force due to gravity. Well, there is what we call gravitational potential energy. We'll start learning a little bit about that in these lessons that go along with chapter 9, but we'll get more into it in chapter 10. But we can store things in gravitational potential energy. There's stored energy from gravity. So if you pick something up, you give it energy. You give it the potential to fall. Okay, so that's one type of energy. Elastic potential energy is maybe like a rubber band. Has some potential, right? So you could stretch it and fling it. Springs also have stored energy, potential energy. And we'll learn about the springs in lesson 23. But we started learning a little bit about springs when we learned about the spring scale and how it has it actually reads the opposite direction as what you're so if you're standing on it, gravity's pushing you down, but the spring force is pushing you up with the equal force, and that's how we get that reading. And then chemical potential energy, well, we have lots of batteries and things we put in everything. And so that's some stored energy so that we can use the energy to do something later on. And so we'll learn a little bit more about chemical potential energy in Physics 152 as well when we deal with batteries. So energy can be transferred, it can be transformed into other types of energy. And so, for example, we have electrical energy can be converted into mechanical energy. So that's the idea behind electric vehicles. And so we have the electrical energy, and then it turns it into mechanical, which is basically that potential or kinetic. Okay, and with a car, it's a kind of kinetic energy, right? We want the car to move, and we need energy to do that. Okay, we can convert mechanical energy into thermal energy or heat. Okay, so the motion of rubbing your hands together is mechanical, it's motion, and you get some heat out of it. Okay, another one is a roller coaster. We're dealing with potential energy and kinetic energy. So when the roller coaster reaches the top of its first hill, it has some potential to fall. And as it falls, it's converting it into, it's losing that potential energy again, but it's turning it into kinetic energy, energy of motion. And that's what makes the ride exciting. So if we define a system, we learned a little bit about this already, a system and an environment. And if we define a certain system to consist of certain things, and separate it from what we call that external environment, then we can do something where we could say that the total energy remains constant. Okay, so for instance, in the roller coaster, if we define the system to simply be the cars, right, all those cars that are hooked together, if that is the only thing in the system and the actual track itself is external, well, then we can say, that this is isolated, the system is separate, and so all the energy that's happening remains constant. Okay, so if we have a certain amount of potential energy here, then it will come down and will turn all into kinetic energy with no loss. But we know in real life there's loss. Right, there's going to be friction between the track and the wheels or whatever it's rolling on. So we know that that's going to be friction, which friction creates heat, that thermal energy. So in reality, we always have friction, and we can't ignore that. But we can sort of do this thing, like we've been modeling this whole course, where we can just say, well, let's pretend it doesn't exist. Since it's such a small amount, we can just pretend it's not there and make our lives and our calculations a bit easier. Okay, so so this is what we mean by we say, and you might have heard, energy can't be created or destroyed, right? Only transferred or transformed. Okay, so the total energy that the car would have, the roller coaster cars would have, would remain constant. There would be a total, and it would just bounce back and forth between potential and kinetic, if that's all we were isolating and worried about. Okay, and so we could say then that, well, there's this kind of thing that raises the cars up to that first peak, and so that's doing some external work on the car. So that's kind of external to the system. And so to start with, we're going to keep things simple. We're only going to consider work to be the only thing that energy transfer process. Okay, and and so work, it is an energy transfer process, and it transfers energy by mechanical means. Okay, so it's work is a bit different from what we define in English, what we mean by we're saying we're doing work. So let's define what work is when we're dealing with it in physics. So when you kick a ball, the force your foot causes, the force of your foot causes the ball to accelerate, right? So you transfer energy when you kick the ball. Your foot is doing work on the ball, okay, and gives the ball some energy, okay? And specifically here, we see it's now moving with kinetic energy because the ball is moving. Okay, so we can consider the ball to be the system, and your foot, or the force that your foot provides, that force can be the external environment, okay? it's doing work on the ball. So the work done by the force of your foot, however much work is done, is equal to the energy gained by the ball. Okay, and in the ideal world, right, where there's no friction and everything, but we can model it as that. Okay, so the foot is doing work. Right, our ball is our system, and your foot that's doing work, that can be the external environment. Okay, and so the amount of work that your foot does is equal to the energy gained by the ball. And so we refer to this relationship as the work energy theorem, okay, where we say that the amount of work, which we'll represent with a capital W, is equivalent to the change in energy. And we're familiar with the Greek letter delta to refer to change. And we use capital E just for energy in general. So before you kick the ball didn't have any energy. But after you kick the ball, it now had a certain amount of energy. Okay, and so the object is moving as a result, and so of this work done, and so we call that kinetic energy. So the energy comes from the energy gain is due to the fact that the force was applied over a certain distance. Okay, so it's not like the foot had to physically touch the ball. Okay, and it was in contact with the ball for a certain amount of time and over a certain distance. Okay, so there's a certain distance that the kick is being applied to the ball. Okay, so to determine this relationship of work, so to determine basically how we can define work as far as this force over a certain distance, we can do this mathematically by applying or putting Newton's second law, the F equals ma, in terms of displacement and instead of acceleration. So instead of acceleration, we could say, all right, force is mass times change in velocity over change in time, right? Or m dv dt. Okay, and if we want to get this in terms of displacement, okay, we can apply the chain rule here. We could say, of course, we have m there, so force. All right, so m, we could say dv dx dt. Okay, applying the chain rule. So if you haven't learned that already, hopefully you have though. And so we're left with m v dv dx. Okay, and so now we see here we have an f force and displacement term, and so I'm going to put those two together. F dx equals m v dv. Oops. Okay, and so this side of the equation that we've just created, f dx, we define this quantity to be work. Okay, so this is work. When you exert a force over a certain distance, that's work. Okay, and this whole relationship here is another way we can represent the work energy theorem. And so graphically, the displacement or the work is the area under the curve of a force versus position graph. Okay, so we're familiar with doing area under a curve on a graph to get some information. So if we graph and plot force versus position, we can find out the work done. Okay, so if the force is not constant, if the force varies, well, we can find the sum if the sum of all those, remember those infinitesimal little bits amount done. So let's say if we have, I'll have the previous slide, we had that, right? So we have this force here, it's changing. Okay, it's not a constant force, it's a varying force. And if we want to figure out, right, what that is, well, we can, remember we did all those infinitesimally as they gradually, those delta x's get smaller and smaller. We find the limit, that's the integral, right? Finding the sum. So the work done, right, when we have a variable force, there's an integral of f dx, okay, from some initial position to some final position. Okay, but on a graph like this, right, it's just it's changing at a constant rate, so we can actually look at this graphically, right? Just as the area, so we don't actually have to do an integral. But if you had some sort of, maybe it was like this in red here, well, then we would have to apply an integral, right? Because we can't just find the area under the curve there. Okay, if the force is constant, okay, so let's say we just have a constant force of 3 newtons there. Okay, then the force is constant, so we can actually factor it out of the integral. Okay, and then so this would just end up being force times x final minus x initial, which we know to be delta x. Okay, and then this is a simple area under the curve as well, right? Force times length times width, force times displacement. Okay, so we're only going to deal mathematically with constant forces. So we're not going to be actually using these integrals. And then when we do have a varying force, we're gonna deal with it graphically, because we know we can easily find the area under the curve if it's changing at a constant rate. Okay, but we're not going to get into this kind of changing force like that. Okay, so we're just kind of making some showing you how this all connects, how the calculus connects to the physics. All right, so let's try a couple of examples here of applying this. How do we do work? And so we have a horizontal rope with 15 newtons of tension, dragging a 25 kilogram box, 2.0 meters, and across to the left across the horizontal surface. So how much work is done by tension? How much work is done by gravity? Okay. So we know that tension and gravity are forces. And so anytime we have a force and it moves over a certain distance, it does a certain amount of work. So let's say we have this box here and it's moving to, let's say we have a horizontal rope, pulling to the left with a tension. So the tension is 15 newtons force. Okay, so it's being dragged horizontally. The tension is being pulled horizontally. And it moves over a distance of 2.0 meters. Okay, so how much work is done by the tension? Well, we know that work is just the force times the displacement. Force here is the tension, 15 newtons, and the displacement is the 2 meters. Oh boy. And so that will give us 30, and the units we see are Newton meters. So that's a perfectly fine unit for for work. But we can also call the Newton meter a joule. Okay. Joule. Okay, or capital J for an abbreviation. And this is important because we'll also come to see that the unit of energy, SI unit of energy, is the joule as well. And we know that work and energy are related. Right? We just saw previously that the work energy theorem is that work is equivalent to the change in energy. Okay, you kick that ball, you do some work on the ball, and it gives some energy. Okay, so work and energy are essentially equivalent, and so that we tend to use the same units to describe them. Okay, so when we have a nice constant force, okay, like we have here, then it's just the force times the displacement. That's it. That's all the work is. Okay, so we can look at this graphically. So here we have a force versus position graph. And we could say that this graph is representing an object moving along the x-axis, so nice and horizontally. And so can we figure out how much work is done on this object during each of these one meter intervals? So from 0 to 1, 1 to 2, 2 to 3. Okay, so we know that work is force times displacement. So I'll call this work 1. So from 0 to 1, it's a constant force. Okay, force times displacement, or base times height, or length times width, whatever you want to call it. And so the force we see is a constant 4 newtons. And the distance is just that 1 meter. Okay, so that's just 4 Newton meters or 4 joules. Okay, and so how about the work from 1 to 2? Okay, again, it's F delta X. And so what do we see happening here? Well, we see there's 2 parts, right? Between 1 and 2, between 1 and, we could just assume that that's 1.5 right there. So between 1 and 1.5, we're still moving at that 4, or being having that 4 Newton constant force applied. So let's just do between 1 and 1.5 first. So it's the 4 newtons for half a meter. So that will give us 2 joules. And then the work from 1.5 to 2. But what do we see here? Now it's, right, we see the dotted line is basically because we're going to model this as essentially going from exactly 4 to -4. Okay, well, where in reality we know it's going to be a curve there, but then we'll have to deal with integrals and stuff. So to just model this as going straight from 4 to -4, then between 1.5 and 2, we're going -4. Okay, so force times displacement, -4 newtons for half a meter is -2 joules. And so what we see then is that, right, between 1 and 2 meters, there's a network of 0 that's done. Okay. And then finally, between the work done between 2 meters and 3 meters. Okay, now we see it's not a constant force. It is a varying force, but it's changing at a constant rate. Okay, so we know that we could do that by the area, which would just be area of a triangle, right? 1/2 base times height. So so then that would be, right, the height would be -4 newtons. And that's again a 1 meter interval. Okay, so then it's basically -2 joules done during that 2 to 3 second interval. Okay, so the negative It's all moving in the same direction positively, right? Going along the positive x-axis, but we have some positive force and some negative force. So maybe one's pushing one way and negative is pushing the other way or pulling. All right. So we looked at the first part, the first side here, the FDX, which is the term for work. And we saw earlier that work is just the change in energy, right? So that means this other side, this MVdV, must be the change in energy. Right. So this is just a couple ways to write the work energy theorem. And so again, if the force is changing, then the velocity is changing. So then we'll have to use an integral to find the sum. Okay, so we'll just look at that right side now. Integral of mv dv. Okay, from some v initial to some v final. And we can simplify this a bit because we know the mass is not going to change. Mass is a constant, so we can pull that out of the integral. Okay, and then if we want to evaluate this integral, then we'll have, let's see, m, and we'll have 1/2 v squared, evaluated from v initial to v final. Okay, and so what that ends up being is 1/2 mv final squared minus 1/2 mv initial squared. Okay, or just 1/2 m delta v squared. Okay, so as this is here is in terms of velocity, then this is actually how we can express, describe, quantify an object's kinetic energy. And so sometimes we make it even more specific, not just to say that this is the work energy theorem, but it's the work kinetic energy theorem. Okay, so we might say work equals delta K. It's another way to express that. And so for our purposes here, since we're mathematically only dealing with constant forces, then we can kind of rewrite this as F delta X is equivalent to 1/2 m delta V squared. Okay, so this will be important to keep in mind as far as the work energy theorem. Okay, and then the direction or the sign of work. So what do we define as positive? What do we define as negative? Well, for positive, if the force is causing the object to gain speed or gain energy, we will call it the positive direction. If the object moves in the same direction as the applied force, we can refer to it as positive. And if it's negative, well, the force, we might call it negative if the force is causing the object to slow down or lose energy, or if the object moves in the opposite direction of the applied force. Okay, so if here we are, if we're pushing a box maybe to the left, okay, so we're applying a force to the left there, we're doing work on it because it's moving. Well, then the work done's positive because it's gaining speed, it's gaining energy, it's moving in the same direction as the applied force. Okay, and so the work done by the person on the box would be positive, but in the ideal world, there's some friction between the box and the surface it's sliding on. Right, we know that friction points the opposite direction of the motion. So actually here, the friction or the work done by friction, and friction is a force, so it can do work, that the friction, the force of friction, the work done by friction would be negative. And there's certain situations where we can have zero work. So let's say you're pushing on something that can't be moved, maybe a wall, maybe a car, which you probably cannot push by yourself on a flat horizontal surface. So if you push and push all you want and the car doesn't move, well, there is no displacement, right? And according to work, it has to be force times displacement. So technically you did no work. And that's where you might say, well, of course I did work because I'm sitting here, I'm sweating and my arms hurt. Well, yeah, you did work. Yes, you definitely did work, but what did you do work on? You did work on your muscles, okay? Your muscles are actually expanding, contracting, right, when you're trying to push. And so you did do work, your muscles did work. Okay, but as far as the car, no work was done on the car, right? Because the car gained no energy, right? It didn't move. It didn't move over any distance. It got no energy, so it got no work done on it. Okay, so that's where the definition of work and physics versus English is a little bit tricky to think about. Okay, and then, oh, and I think I actually forgot to do this in the previous problem. We found out how much work was done by, up here by the tension, but the second part was how much work was done by gravity. Okay, and so you think about that here. Well, even if the car did move along a flat horizontal surface, how much work did gravity do? Right, gravity is a force. Right, so the work done would be mass times gravity, and I'll just use delta y since gravity always pulls vertically. Well, if there's no vertical motion, right, there's also no work done. So if you pulled something horizontally, like in that problem we looked at here, no work done. Okay, there was no work done by gravity. So the work done by gravity is 0. All right, so what we did calculate was the work done by the tension. But gravity, if it's not moving vertically at all, it does 0 work. Okay, and then we can also, we've talked about net forces, so we can also have net work. And the important thing about work done is we always have to define it to be what's only done, the component of the force that's parallel to the motion. Okay, so I'll write that down. So the work is only done parallel to the applied force. Okay, so what that means is that we see this person here pushing, applying a force. He's pushing this, trying to slide this object horizontally, but he's not pushing perfectly horizontally. He's pushing up at a little bit of an angle. And so the only component of the force that's going to actually contribute toward the work done on the object, or the energy gained by the object, is what's parallel to the direction of the motion. Okay, so we can draw the free body diagram of this to see and calculate that. And so the force they're giving us here is F1. Okay, and then they're giving us an angle here, 15 degrees. And so the component parallel would be, we can call it F1x, or the x component of F1. And we know that that's going to be, if we do cosine of the angle, it's going to equal adjacent over hypotenuse. And so that x component is just going to be F1 times the cosine of 15 degrees. Okay. Okay. Because if you think about it, if he's actually pushing like this, in a way, he's sort of partially lifting it too, right? and we've seen this before, like when friction, when we did the person being pulled on a sled, and we found that we had to find the component there because he was partially lifting the sled. Okay, so there wasn't as big of a normal force because of that. So the same thing here with work, even though it's, you know, you're not really lifting it, it's sort of, this person's sort of wasting, right, exerting more effort than they need to. And if this person were to push perfectly horizontally, then you would get more more energy, would be doing more work. Okay, so there would be a more ideal way to push this. If this person had taken physics, they would know this. Okay, so an example of this, we have you throw a 5.5 gram coin straight down at 4 meters per second from a 35 meter high bridge. How much work does gravity do as the coin falls to some water below? And what's the speed of the coin just as it hits the water? Okay, so here it's being thrown straight down. So now we know the work is force times displacement. And this is straight down, so I'm going to use delta y. And so the force here that's doing the work is gravity, the force due to gravity. So I'll write that's mg delta y. Okay, and that's 5.5 grams, so that's going to be 0.0055 kilograms. Put that into SI units. And let's see, gravity is 9.8. And the distance traveled is 35 meters. Okay, so doing that, I get 1.9 joules. Okay, and then the speed, well, how fast is it going? Well, here we know it's falling under the influence of gravity. Okay, we've given it an initial speed though, right? 4 meters per second, and so we can apply the constant acceleration model to find out what speed it hit the water with. Okay, so we can use for this situation the v final squared equals v initial squared plus 2a delta y. Okay, and so it'll be a square root of vi squared. So the initial speed was that 4 meters per second plus 2, and the acceleration was gravity. And the delta y, the 35 meters. Okay, and I get about 26.5 meters per second when I did that. Okay, and one thing we can do is we can actually use what we found out here, this final speed that we found out here, to check what we calculated for work. Right? Because remember, what we learned was that work is equivalent to the change in kinetic energy, which is 1/2 m delta v squared. Okay, which would be 1/2 m v final squared minus v initial squared. Okay, and then again, that mass would be 0.055 kilograms. Final velocity 26.5 meters per second. I'll square that. Minus the 4 meters per second initial velocity squared. And if you do that out, you'll also get 1.9 joules. Okay, so here's probably half the homework is from this lesson from chapter 9. And there's one example problem if you want a little extra help that goes, that one's dealing with one of the force versus position graphs. So if you're having trouble with that, I think it's 22 in the homework. If you're having trouble with that, this one would probably be very helpful. And so did we learn to determine the work done by a constant force and a variable force? Well, we saw that for a constant force, we can just find the force times the displacement for the area under the curve. And for variable force, we're only going to deal with that graphically. We have a constantly changing force, right? And that's just going to be the area under the curve. And did we learn to quantify the energy due to motion of an object? Well, we found that kinetic energy of motion, we found that to be 1/2 m, 1/2 of the mass times the change in velocity squared. Okay, and we also saw that work and energy were related. They're essentially the same thing. And so we can write that work energy theorem as work is equal to change in energy, or work is equal to change in K. And then we also have another way to write that, right? Work is force times displacement and equals also kinetic energy. Okay, that's all them for lesson 21.